Okay, this is about human input and output. After we've done all of our collection of things that are problems, we need to look at how people actually receive and generate information so that we can deal with that appropriately. So what we have is we have a user interface. On the left side we have a user. On the right hand side we have some software. In between is that line which represents our interactive computing device. So our software is going to generate a presentation of its current state or its data, and it's going to present that on the device. Now this might be a screen, this might be audio, this might be some other form of presentation. The human being has to take whatever is presented and perceive it, and based on what they perceive, they will make a plan for what they want different, what they want changed, and they will express themselves using one of their natural means of expression. What we then have to do is interpret that expression, and based on that interpretation make changes to our software, which will then make changes to the presentation, which will be perceived by the user, which will cause them to make a new plan and express a new desire, which we'll interpret, and round we go. Okay, the key for our problem that we want to talk about today is these two steps: human beings perceiving and expressing, because that's the key to building an effective user interface. So we need to look at that. Okay, so human input. How do we get information into a human being? We have eyes, ears, touch, smell, taste. 5 senses. We learned that in grade school. But let's go through and look at what the bandwidth is. That is the amount of information that we can actually transmit into a human being through each of these channels. So let's start with our eyes. We have 2 eyes. We get about 1 megapixel per eye. It takes 3 bytes per pixel, and we get about 30 images per second through our eyes. So if we do the arithmetic, we come up with our eyes can receive 180 megabytes per second. That's pretty good. That's a lot of information coming in pretty quickly. Okay, our ears, they can sense up to up to 18,000 cycles per second. So that's 18 kilohertz. Now, if we do Nyquist sampling, we have to sample twice per cycle. More would be better, but we're going to take the small end here. And using CD recordings, we're going to take 2 bytes per sample. And then we have 2 ears. We multiply that all together, and the ears are 144 kilobytes per second. That's the total information that can come in through our ears. Now, if you look at the difference between eyes and ears, it's almost 1,000 times different. In fact, it's more than 1,000 times difference. So that's a huge disparity between what our eyes can bring in and what our ears can bring in. Okay, let's look at touch. Your touch, you can sample about 25 touches per second, and you have 10 fingers. That arithmetic's easy. 250 bytes per second. Almost 1,000, not quite 1,000 times slower than ears, and 1,000,000 times slower than eyes. Okay, so this little quick analysis tells us that eyes are definitely winning here. Now, taste and smell, we're going to ignore them completely for a number of reasons. The first reason is we don't have a good mechanism for generating tastes or for generating smells. There are some experiments, but they're not very good. So we don't have a technology. Second thing is the bandwidth, that is the amount of information, is very, very low. Once you put a smell in the air, it takes a while to get that smell out of the air. Is anybody who's ever run over a skunk? They know this. Okay? Similarly with a taste. You get a taste in your mouth, it's going to take you a while. It's going to be a matter of seconds or minutes, not a matter of thousands of times per second. So taste and smell, they're not going to be very much use to us to interactivity. Alright, let's go to human output. Here's our big 3. We have speech, which is people can talk. We have typing, and then we have gestures. And particularly we're going to focus on being able to point. So let's start with speech. The usual person can speak between 120 and 160 words per minute. There's about 5 characters per word. Do that and we come out with 14 bytes per second. This is enormously slower than what we're able to sense. 14 bytes per second. That's how much information comes out when I talk. Okay, typing. You can type about 90 words per minute if you're a good touch typer. The world record is 216, but there are almost nobody can do that. And again, we've got 5 bytes per word. So if we type, we're at 7.5 bytes per second. Almost half the speed of our ability to talk. Okay, now speed and speech and typing are a bit problematic. We have the technology to sense keystrokes, and that's extremely accurate. People are a little error prone in the way they type, but we're very accurate. We have technology to sense speech, and it's not very accurate at all. And the reason for the inaccuracy is because we're trying to translate an audio signal into the information. It turns out to be a very hard problem, and for which is subject to a lot of things like ambient noise and a number of other things, and that hasn't quite got there yet. Okay, gestures is mostly for our purposes about pointing. Sometimes we'll use gestures for writing and drawing and things like that, but our big use is for pointing. Now the thing we want to think about when we think about gestures is we want to think about dexterity. In other words, how fine are the manipulations we can do and how fast we do. And one of the things that controls dexterity is how big is the muscle doing the control divided by how big is the thing that it's controlling. Alright, so it turns out your highest dexterity is actually your tongue. It's actually impolite to point with your tongue, so we don't do that very often. Next one comes your fingers. And if you look at your fingers, you have little tiny skinny fingers, but the muscles that actuate those fingers are in your fingers. The muscles that actuate those fingers, if you flex a finger and watch, is up in your forearm. That muscle is actually up near your elbow, and it's 2 to 3 times bigger than your finger is. So the muscle size to the size of things that are moving. So what that gives me is lots and lots of muscle to control a little tiny thing. That's why we draw and paint and do all sorts of things with our fingers so well. Next one is the wrist. Okay, the muscles that move the wrist are about the same size as the muscles that move the fingers, except that your hand is a lot bigger, so you're not as good if you turn it into wrist movement. So for example, if you grasp a mouse and try to draw with it, it's very difficult. And the reason is because the size of your hand compared to the size of the muscle is not good. Now, if you look at farther up your arm, your forearm is actually controlled by your biceps and triceps in your upper arm, and those muscles are almost the same size as that arm. So anything you have to do with a large movement with your arm, not very dexterous, not very accurate. Now, this is not a mathematical relationship, it's just one that's easy to think about. So your dexterity, useful for our purposes, is in your fingers. Okay, so quick summary of human input and output. We've got our eyes, 1,000 times less as our ears, and 1,000 times less than that is touch. For output, we've got speech. At half that speed, we've got typing, and at much slower than both of those, we've got gestures and pointing. These are the things we've got available to us to use. What we're going to focus on is eyes for the input and typing and gestures for the output. Those are the things for which we have good technology, and we also have good dexterity. So there it is, human beings and the information we need to know about how we get input and output from them.